In this section of our text, we begin visiting something known as Hess's law, those relationships involving the heat of a reaction, delta H. When reactions are multiplied by a factor, the delta H of the reaction is multiplied by that same factor. Recall that delta H is extensive. That term simply says it depends upon quantities. How much you have will affect, as in what I just fixed in the last example, the amount of reactant and product will affect the size of delta H. The term extensive, mass is an extensive property. It changes with the amount of matter you contain. Let's suppose in this example, here's that combustion of diamond. Carbon as a solid combusts and produces carbon dioxide. Its heat energy that's released is negative 393.5 kJs. Suppose I double the amount. Doubling the moles will also then double the delta H. Twice the heat energy is then released. The same is true as if I tripled it. Whatever I did to distribute through coefficients, I do the same to the delta H. If I half it, I take half the delta H. If the reaction is exothermic in one direction, I flip the direction of the equation. The reaction is written in the reverse order. The sign also changes from negative to positive. If the reaction is reversed, the sign of delta H is opposite. Endothermic in one direction creates an exothermic in the opposite direction. These relationships involving delta H are known as Hess's law. Hess's law simply states the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. If the heat of reaction of step 3 is the sum of step 1 and step 2, the heat of reaction for step 1, when added to step 2, gives me the complete change of step number 3. The heat of reaction for an overall reaction is the sum of each individual step along the way. If chemical changes occur in a step-by-step fashion, we simply can add those steps together to find the overall equation. Let's model a Hess's law to see if that helps clarify. An example of Hess's law. Let's examine what we called elementary reactions. Elementary reaction 1, 2 units of NO combine with 1 unit of oxygen to form 2 units of NO2. An exothermic process, 116 kilojoules of heat released. Elementary reaction number 2 says 2 molecules of nitrogen react with 5 of oxygen and 2 of water to form 4 HNO3s, an exothermic value. And there's a third elementary reaction. Nitrogen and oxygen form 2 NOs. It's an endothermic process. What Hess's law is asking us to do is to combine these 3 equations so that when it's simplified, just as in algebra we can simplify things that are on the same or opposite side of the equal, we can do that as well with chemical equations. What we'd like to do is to be able to add these 3 equations so that when I simplify them, they give us the target. And that's what I refer to as this bottom one. This is our target equation. How do we build 3 units of NO2 plus 1 water, giving us 2 HNO3s and 1 molecule of NO? So I look at the first reactant in my target equation for no other reason than it's written first. And here's what I notice. I'm going to start going through my equations and see where it's written. I notice that NO2 is a product in the first equation. Is it written anywhere else, or is that the unique place? I don't see NO2 written any other place. So here's what I like about it. NO2, its unique position. So now that gives me some ideas of what we're going to need to do with this particular equation. It's on the wrong side of the arrow. It's supposed to be a reactant, but I see that it's a product. And instead of 2 units, we're supposed to have 3 units. Alrighty. What do I multiply 2 by to get to 3? 2x equals 3. So x, of course, is 3 halves, or 1.5. What I think I need to do is not only flip the direction, then I'm going to have to take 3 halves to distribute. And so when I do that, think about the delta H. You're going to flip the sign and multiply it by 3 halves. Let's pause and do that together. We're going to flip the direction. So 2 units of NO2. 2 times 2 is 6. 6 over 2 is 3. So 3 halves times 2 gives me the whole number of 3 units of NO2. Then the arrow. 3 halves times 1 is 3 halves oxygen. And 3 halves times 2 gives us 3 units of NO. The delta H for this equation, we flipped the signs because we flipped the direction. And let's just simply hit 3 halves of 116. And I get 174 kilojoules of heat. So what I've done so far is just examined the first reactant, NO2. The unique position in my building equations, these elementary reactions, was in the first target equation here. The NO2 was written as a product. It's on the wrong side of the arrow for my desired location, so I knew to flip the direction. I also had the wrong amount, so I took a fraction. 3 halves of 2 gives me the desired amount found in the target. So I flipped the direction and distributed a 3 half. When I flipped the direction, I flipped the sign on delta H, and I distributed 3 halves through the 116. Let's go on and examine the second reactant in our target equation. The second reactant is water. Let's begin skimming through our building equations to see where we locate water. I find it in the second equation, and it's the only place I find water. I like the side of the arrow it's on. It's on the left side as it is in the target, but I have twice the number that I need. So I'm going to leave the direction alone, but I'm going to distribute 1/2 through that equation. I need half the number. So let's do that together. 1/2 of 2 is 1 molecule of nitrogen, plus 1/2 of 5, I'll just write as 5 halves oxygen, plus 1/2 of 2 is a single water, 1 water. Then we have an arrow. 1/2 of 4 is 2 HNO3s. Let's adjust the delta H. Distributing 1/2. Now I'm going to leave the sign the same. It's still negative, but 256 cut in half is 128 kilojoules. All right. Let's see what else needs to happen. The HNO3s, that's the first product, I believe we have taken care of. I see it on the product side in that second elementary reaction, and we have the desired amount. We have 2 units by cutting the half from up above. We have the product NO, which appears in a unique position in number 3. No, it's not unique. I see it in equation 1 and equation 3. Alrighty. Now equation 1 we adjusted. Remember, when I stare at the original equation, there were 2 units that might appear that we wanted to cancel those out, and they would have, except we had to adjust that first equation. So leave the third one alone. Let's just rewrite it as it is. Leave it alone. N2 plus O2 gives us 2 NOs. And I didn't do a darn thing, so I'm just rewriting the delta H, positive 183 kJs. If we add these equations together, simplifying anything from the opposite sides of the arrows, cancel them out just as you would in algebra. Here's what I'm finding. I have on the left side of the arrow, let's see, nitrogens are combining. Well, interestingly enough, this number 3, I think I made a mistake. But examining is always the secret to figure out if we've done this correctly. What I noticed is there's no nitrogen in the target equation. You probably noticed that right away. The nitrogens have to disappear. Right now, my equations are combining them. That doesn't make sense. I think I need to go back to the drawing board and flip the direction of the third. And if I flip it, I got to change the sign. Back the bus up. Let's rewrite the third equation in the opposite direction. I bet magic happens. 2 NOs yields N2 plus O2. Now I'm seeing it. All right, new color. Here's what we've got going. N2s now cancel. I have 1 molecule of N2 on the left in equation 2, 1 on the right in equation 3. They cancel. What else might cancel or simplify? I have, how about here? 2 molecules of NO on the left in equation 3, 3 molecules of NO on the right in equation 1. That can be simplified. And that's the whole reason I knew to flip this one. 2 units of NO leave me a net remainder of 1 NO in that top equation. Here's what else we see. On the left side of the arrow in equation 2, there's 5 halves of oxygen. On the right side is some oxygen in both equation 1 and 3. 3 halves and 1 whole more is the same as 5 halves. Think of this as 2 over 2, and you can simply add 3 plus 2 to make 5 halves. That's going to simplify, and the oxygens are all gone. 5 halves combined on the right can simplify with the 5 halves written in equation 2. And I think we've got there. I had one little flip in equation 3 that I had to repair, but here's what's left over. Equation 1 has 3 units of NO2. That's the first target reactant. I see in equation 2 a reactant, and that's the water molecule. That's cool, because there it is. It's in our target. Those are the only 2 reactants left over, and they match the target. Let's look to the right side of the arrows. I have 1 molecule of NO that did not cancel out, and that's in our target, and 2 molecules of HNO3. This indeed matches the target equation. The only thing left to do is to sum the 3 delta H's to get the new equation. Add together what we've calculated. So positive 174, let me show the calculator, plus negative 128, plus a negative 183. And the heat of our reaction for the target equation is negative 137 kilojoules of heat. Hess's law, little puzzles. What can I do with these elementary reactions so that when I combine them back and simplify, I've built the target? I like them as little mental practices, little puzzles. Obviously, I got to keep trying if something isn't working. Pause the video, take a look at this next practice, and when ready, play it. Here's our next practice in Hess's law. Let's see if we've reached a common answer. As I read the first elementary reaction, copper is combining with chlorine to produce copper 2 chloride, an exothermic reaction. Second equation, 2 coppers with a chlorine produce 2 units of copper 1 chloride. Different names based on the charge of the copper. Again, an exothermic process. How can we combine these 2 reactions to form the target equation? Building from these 2, let's create the target. Well, again, I like to start, for no other reason than it's written first, with the first reactant in the target equation. Here's what I like about it. Copper as a solid is written on both sides of the equal here, so it's not in a unique position. The first reactant I'm really not finding too helpful to get any ideas what to do with the elementary reaction. Let's see if we can find something else unique. Here is copper 2 chloride as a solid, and that particular reactant is in a unique position. Only one of them appears, and it's in the first equation. I like how many I have, but it's on the incorrect side of the arrow. So I think what I'm going to do is rewrite this first equation and flip its direction. So CuCl2 as a solid, we'll go to Cu as a solid and Cl2 as a gas. Since I flipped the direction, the delta H goes from negative to positive 206 kilojoules of heat. Let's see what else we have. The product is 2 copper chloride solids. Well, that's exactly written in the correct position in that second equation above, and it's the correct number. Could it have been as easy to flip the first and leave the second? Let's take a look. If our strategy indeed is correct, it should simplify to create the target. If I flip the first, leave the second as is, let's see if indeed it simplifies. I notice chlorines will cancel out. It's a product in the first equation, a reactant on the other. They will cancel. I have 1 unit of copper solid, 2 units on the left in the second equation. That's going to give me a net of 1 copper. I think it really was that easy. 1 copper is remaining, plus copper 2 chloride on the left side of the arrow, giving us 2 copper chlorides, the only products left in our equation. All we have left to do is to add to find the new heat of reaction. We'll take positive 206 and add a negative 36. I'll try that again. Positive 206 plus a negative 36, and we get 170 kilojoules of heat energy. Perfect. I hope that matched yours. Our next topic to be covered is called standard conditions. The standard state is the state of a material at a defined set of conditions. For instance, of a pure gas, the standard state would be taken at exactly 1 atmosphere of pressure. A pure solid or a pure liquid in its most stable form at exactly 1 atmosphere of pressure. Standard pressure is typically 1 atmosphere. From our gas law units, perhaps you remember other pressures. 760 millimeters of mercury, we called torr, is another standard value. 101.3 kilopascals is another standard value, which happens to be the metric system. Standard pressure is going to be defined as the standard state of any solid, liquid, or gas as its natural condition. Temperature is given as room temperature, 25 degrees Celsius. And the standard state of a solution is taken as 1 molar, 1 mole per liter. Standard enthalpy change is now going to be given just a little symbol to represent that we've been measuring this in a standard state condition. And you'll just see that with a super knot after the H. Defined as the enthalpy change when all reactants and products are in their standard states, running the reaction at standard pressure and temperature of 25 Celsius. The standard enthalpy of formation, given with a sub F after heat of formation, the enthalpy change for the reaction forming 1 mole of a pure compound from its constituent elements. Constituent means just what are those made up from the compound. The constituent elements of carbon dioxide would be carbon and oxygen. Found in the natural state, carbon is written as C, it's a solid. Found in its natural state, oxygen is the diatomic molecule. Forming a compound from its standard state constituent elements is called the heat of formation. Pure elements are not made in nature. That's what we find and build compounds from. If a pure element in its standard state is found in nature, it's just given a value of 0 kilojoules per mole. That's the very definition of heat of formation. We do not form elements, we build compounds from them. Here's a chart that deals with the standard enthalpies of formation. Bromine, for instance, is a liquid at room temperature, and it also is one of the lucky 7 diatomics. Notice it has the value of 0. The natural state of bromine is a liquid in a diatomic form. A single atom of bromine in a gaseous form takes energy to build. We'd have to split this molecule to create the unnatural state of atom bromine. Here's calcium as a solid. That's the way we find it in nature. It has a value of 0. And I see compounds listed, how much energy it takes to build those compounds from the elements it's made of. In nature, carbon is typically found as graphite, which is like pencil lead or a lump of coal, given a value of 0. It definitely takes energy to create diamond, and you can see it has a positive 1.88 value, and so forth. So here's a list in a somewhat alphabetical order of standard enthalpies of formation. I'm going to keep this chart handy. We'll be using it as we do some of our math problem examples. So formation reactions, it simply says reactions of elements in their standard state, the way we find them in nature, to form 1 mole of a pure compound. If you're not sure what the standard state of an element is, we have an appendix in the back of our textbook 2B that has a heat of formations for those pure elements. And again, I happen to have one in front from the previous slide. That one was taken out of our table 6.5. The appendix in the back of your book has a much more extensive list. Because the definition requires 1 mole of a compound be made, the coefficients of the reactants may be fractions. To clarify, suppose I want to build 1 mole of a molecule called carbon monoxide. 1 mole of carbon will react with half a mole of oxygen to create 1 mole of carbon monoxide. So fractions are allowed, simply reading in terms of mole values. The formation of a reaction is the reaction between the elements in the compound, which are carbon and oxygen. But the elements must be in their standard state. We do not find oxygen as an atom in nature. It's too unstable. Instead, we find it as a diatomic gas, and we use the oxygen molecular form to create compounds. And notice what they've done here to keep it balanced, to produce just 1 mole of a molecule of carbon monoxide. We took 1/2 a molecule of oxygen and combined it with carbon in the graphite form. Carbon, in its natural state, is graphite. The heat of formation is 0. Again, if you're not sure, it's found in our appendix. Oxygen, in its standard state, is a diatomic molecular gas. It is 0 when it's O2 as a gas, and I don't see it written any other way, so that's my only choice, to write it as O2 as a gas. So what might be some heats of formation reactions for the following? Here's an example. If we wanted to create a formula showing the formation of carbon dioxide gas. Carbon is in the form of graphite, heat of formation of 0. Oxygen in its molecular form as a gas, heat of formation of 0. Carbon dioxide as a gas is formed from its constituent elements. And I literally can just simply look up carbon dioxide in its gaseous form, negative 393.5 kilojoules of heat. Delta H would be negative 393.5 kilojoules per mole of CO2 formed. The carbon dioxide value built from its natural state elements. This thermochemical equation is exothermic. Suppose we want to produce aluminum sulfate solid. Aluminum sulfate is actually built of 3 different elements: aluminum, sulfur, and oxygen. Aluminum in its natural state is a solid. Sulfur in its natural state is rhombic. S8 is its natural state. How are we supposed to know that? Well, I check it out using my enthalpy of formation. The standard state, the way we find it in nature, has the 0 assigned to it. And notice it's a rhombic, which is just a geometric pattern of how we find sulfur atoms bonded together. We had diatomic molecules, such as oxygen, fluorine, chlorine, bromine. There were 7 of those. This has 8 atoms bonded together in a rhombic geometric pattern. So this has an assignment of 0. And again, oxygen as an assignment of 0. When the 3 natural state elements combine to form the compound, aluminum sulfate is produced. The fractions here, or coefficients, are simply to create 1 mole of aluminum sulfate. Notice that we're just taking each element individually to build the compound. When we want to calculate standard enthalpy change for a reaction, we need to have access to that table, heats of formation table, either in your appendix or from printing this particular PowerPoint. But any reaction can be written as the sum of formation of reactions. That's Hess's law, or the reverse of formation of reactions. Again, Hess's law, if you flip the direction, we simply flip the sign. So instead of using Hess's law, as tedious that might be, although I find enjoyable, we've come up with an easier way to find a target equation, and that's simply taking the sum of the products minus reactants. Products minus reactants will find the sum of the heat of reaction. That sigma stands for sum, and it's a Greek symbol. Perhaps you're familiar with it. N is the coefficient in front of each product or reactant. So, using our standard heats of formation, we're able to calculate a little easier than using Hess's law. Let's model with this example on slide 41. Methane gas plus oxygen gas, this is a combustion pattern, produce carbon dioxide gas and water gas. This is a balanced equation with a 1 to 2 to 1 to 2 equation. We need to repair that coefficient. Let's go to work and see if my PowerPoint slide has enough or if I have to pull out the back of our chemistry book. Methane is CH4 as a gas. I go to work and I find its value. And I'm just going to write it for now right underneath the equation. I'm going to write negative 74.6. And that's in a kilojoule. Diatomic molecular oxygen is 0. Again, just showing that we know oxygen in its natural state, here it is 0, O2 gas. And again, I would distribute the 2. 2 times 0 is still 0. Carbon dioxide gas, going to our chart, CO2 gas, negative 393.5. And how about water gas, H2O? And water is listed under the oxygen. Water as a gas, negative 241.8, but I have to distribute the 2 through that. All right, so coefficient times the number from our chart. Simply stated, if I want to calculate the heat of this reaction, it's the sum, and I'm not very good at drawing those sigmas, the sum of the products minus reactants. So, products first. I'm going to take negative 393.5 plus 2 times negative 241.8. The sum of the products minus the sum of the reactants. Negative 74.6 plus 0. So here's what we have, just to kind of clarify. First big bracket is product minus reactant. Let's hit on our calculator and see if we can get a common answer. All right. So first set of parentheses, negative 393.5 plus 2 times negative 241.8, close your parentheses out, minus negative 74.6 equals. And I found the heat of this reaction to be negative 802.5 kilojoules of heat. These problems simply have us take time with the standard enthalpies of formation chart, either using your appendix or the slide from the PowerPoint, finding the values, and I just record them underneath just to help me tabulate. I have to distribute the coefficients through. I sum the products and I subtract the sum of the reactants. Products minus reactants will pull out the Kj, the heat of energy for that reaction. Why don't you try one and see if we can reach a common answer, pausing the video and working ahead, turning it back on when ready to check. Here we have C2H2 as a gas. Again, I'm just going to use my chart and find C2H2 is positive 227.4. 227.4. I'll know I'll have to distribute through 2 times that value. It is a positive. Oxygen, again, in its natural state is 0. Carbon dioxide gas, we looked up, negative 393.5. Remembering to distribute a 4 through that value from the coefficient. And now liquid water, negative 285.8. Distribute a 2 through that. The heat of this reaction is the sum of products minus reactants. So I'll just set up my math. The heat of the reaction is found by taking 4 times negative 393.5 plus 2 times negative 285.8. The sum of the products minus 2 times 227.4. And there's the sum of the reactants. Products minus reactants. Let's hit together and see what we find. We have 4 times negative 393.5 plus 2 times negative 285.8 minus 2 times 227.4. We get a value of an exothermic negative 2600.4 kilojoules of heat. Products minus reactants, distributing the coefficients, and simply taking some time to look through the standard enthalpy chart to find your equation. How many kilograms of octane, is this on the right slide? Looks like it. How many kilograms of octane, C8H18, that's gasoline, must be combusted? So add oxygen, out comes carbon dioxide and water, to supply 1 times 10 to the 11th kilojoules of energy. Well, let's balance as I'm counting in my head. 8 carbons, try an 8 there. 18 hydrogens, so I'll try a 9 here. That's going to give me an odd number of oxygens, which is completely fine if we want to care. We have 8 times 2 is 16, plus 9 is 25. To put a whole number here wouldn't make sense because I can't get O2 to add to 25, but I can do a little trick. It's 25 halves. And I don't mind doing that because the heat of formation for oxygen is 0. Any number times 0 is going to stay 0, and yet this still allows me to balance the equation. Alrighty. So, how many kilograms of octane? I guess we're ultimately trying to solve for octane, C8H18. C8H18 isn't on our list, C8H18, but we can solve for it. So suppose the delta H for this reaction is 1 times 10 to the 11th kilojoule, and that's for every 1 mole of octane. Alrighty. if this particular reaction per mole releases 1 times 10 to the 11th kJs, how many kilograms would be released? I look at this more as stoichiometry than really with the enthalpy chart. So if I know that 1 times 10 to the 11th kilojoules of heat are released, well, I don't really know that. I'm going to pause. Let's think this through. What I don't know is that's the delta H, because it does not say that it's in kilojoules of heat. Alrighty. But what if I solved for this, making this the target? I can find out how many moles or kilojoules of octane must be there. If 1 times 10 to the 11th is the heat of the reaction, the sum of the products minus reactants, where I can target the octane, which would tell me its heat per mole, and I can turn that into kilograms with a little mole map. So let's go to work. Carbon dioxide, looking up CO2 as a gas, negative 393.5. And again, a combustion, water will come out as a vapor. I'll use negative 241.8. Oxygen's heat of formation in its natural state is 0. So if this is the whole heat of reaction, that's our target, 1 times 10 to the negative 11th kJs. And that was found by taking the sum of the products minus reactants. Let's make the octane the target. All right, so we'll have to distribute the coefficients. 8 times negative 393.5 plus 9 times negative 241.8. This is the sum of the products minus the sum of the reactants, which we're just going to call X, the heat that's released from this combustion. X. And just solve for that, and we'll look at and call that good. So, all right, let's do a little algebra. 8 times negative 393.5 plus 9 times negative 241.8. And here's what I have, and I'll just rewrite 1 times 10 to the 11th kJs equals negative 5324.2 minus X. Let's add to both sides to simplify. 5324.2, and when we do that, this will still be quite a large number. So 1E11 plus 532.4, still going to be pretty near the same number. So I don't think I want to bother writing all those zeros down. It's so large, it in essence stays the same value. But now I can see that that's what negative X is. And so X really is negative 1 times 10 to the 11th kilojoules. Now I've just verified that indeed that's the amount of heat that came out per mole of octane. It makes sense. Octane is gasoline. We burn it for fuel. A whole lot of heat energy is going to come out. And if that's per mole, and that's what we let X stand for, if this was a 1, we just now calculated the energy per mole. I had that sense that that's what delta H was, but we just verified it mathematically. That the carbon dioxide and the water, even though it really is 5324.2, 5324.2, when I add that to such a large number, it in essence stays the same number. I mean, you could carry all those decimals and it really just wouldn't change the overall answer. We have a little mole map to work to do. Let's take 12 times 8 plus 18, finding the molar mass of octane, is 114. So 1 times 10 to the negative 11th kilojoules, and that's for every 1 mole. 1 mole would have a weight of 114 grams. Moles have canceled, and we're going to get a kJ per gram and telling us how many grams we'd have to burn. And it will not be a large number, and we'll just ask you to flip to a kJ. So 1E11 That's not negative, it's positive 11. Divided by that number, and I'll just go times 1,000, and it's still quite a bit. 8.77 times 10 to the 11th kilograms of fuel would combust to produce such a large amount of heat energy. I think the bigger story with this particular problem, just kind of putting away such large numbers and thinking through the strategy, if we know the heat of reaction and we can look up all but one of the ingredients, we can make that our target variable. In essence, that's all we've really done. The story problem, that probably wasn't the best because they chose such large numbers that the algebra kind of fell apart. Subtracting or adding such a tiny number to such a huge number really didn't change it significantly. But just thinking about the strategy, we knew the delta H of reaction. We looked up the sum of the products and called the target variable X the amount of joules of heat energy per mole of C8H18. Once we solved for the heat energy per mole, we just simply flipped it to find how many kilograms by using a mole map problem. Let's take a look at one more, practicing delta H for a decomposition. When the decomposition of calcium carbonate under standard condition occurs, we have the following set of data. Calculate delta H for the reaction. Well, this one's pretty straightforward. Mass, or the heat of reactants, CaCO3 is given. The products given. So they really have done the legwork. They've looked up, using their appendix, the values for us. And all we're being asked to calculate is delta H. What that will come to is per mole. And we'll just have to find out for the mass of 10 grams. So let's find delta H by taking the sum of the products, which would be negative 634.9 plus 0, the two products, minus the sum of the reactant, of which there's only one, which is negative 1207.6. We'll simplify this for the reaction, and that comes out in per mole. And notice calcium carbonate is already written in a per mole basis. The coefficient is a 1. So here's what we'll do. We'll take negative 634.9 plus 0 minus a negative 1207.6. And that comes out to be a positive value of 572.7. Think about that as just standing for kilojoules of every 1 mole of calcium carbonate. But we didn't have 1 whole mole. We had 10 grams. 10 grams of calcium carbonate can be converted to a mole by using a formula weight of CaCO3. Calcium has a weight of 40, 12 on the carbon, and 16 times 3 on the oxygen, and the molar mass here is 100 grams. So 10 grams is the same as saying 0.1 mole of calcium carbonate. If 572.7 kJs were released for 1 whole mole, how many would have been released for 0.1? Notice then how the moles cancel, and we've got it in kilojoules per 0.1 or 10 grams. So all we have left to do is really slide the decimal. 572.7 times 0.1 is 57.27 positive units, kilojoules of heat energy. Decomposition is an endothermic process. It takes energy to force limestone to decompose. If I had 10 grams of limestone, I would have to put in 57.27 kilojoules of heat energy to force its decomposition. Again, we solve for delta H. Notice it's for every 1 mole of the reactant. We then converted the 10 grams into a mole and decided 572.7 kilojoules for every 1 mole would be 57.27 if I had only a 0.1 mole. The last topic we'll talk about are bond energies. Chemical reactions involving breaking bonds and reactant molecules and forming new bonds to create the products. The enthalpy of a reaction, that's what delta H stands for, is enthalpy, can be estimated by comparing the cost of breaking old bonds to the income from making new bonds. This amount of energy needed to break 1 mole of a bond is called its bond energy. Typically, they are reported in the gaseous state and homolytically, just simply saying each atom gets half of the bonding pairs of electrons. How much energy is needed to break 1 mole of a compound's bond is called its bond energy. The actual bond energy depends on the surrounding atoms and other factors, but we often use what are called average bond energies to just simply estimate the enthalpy of a reaction. These enthalpy of reaction really is just given to us in a chart, and here's one now. It's on slide 71. This is a chart then taken from our chemistry book, table 9.3, and it's just take a closer look. It's telling us how much energy each type of bond is required to just break them in half. If I wanted to break an HH bond, I'd have to put in 436 kilojoules for every 1 mole of hydrogen. If I wanted to break a double bond to carbon, 611 kilojoules of energy is required. So it's just giving us an average amount of energy needed to break a bond. So these average bond energies are reported to us in a table. We simply look them up. Bond breaking is endothermic. Bond making is exothermic. Breaking bonds requires energy. Making bonds releases energy. Important note, if I'm breaking bonds, the sign on delta H is positive. If I'm forming new bonds, the sign on delta H will be negative. The heat of the reaction is the sum of all the bonds broken plus the sum of all the bonds formed. Forming bonds is exothermic. Bond breaking is endothermic. Keep in mind when we read the charts, we'll have to make sure if bonds are breaking on the reactant side, those are reported as positive numbers. Bonds are forming on the product side, those will be reported as negative numbers. Let's take a model problem. Oh, we'll do that in a minute. We'll talk about trends in the bond energies. This is a slide that's saying the more electrons that 2 atoms share, the stronger the covalent bond will be. Notice that a triple bond carbon requires much more energy to break than a double bond carbon compared to even a single bond carbon. The more bonds between 2 atoms, the more energy is required to break that. In general, the shorter the covalent bond, the stronger the bond. Triple bonds are much stronger than double, which is much stronger than single. And remember that resonance structure, the hybrid, would lie somewhere between a single and a double bond. So the amount of energy needed to break a resonance structure is a little different as well. In general, the shorter the bond, the stronger the bond. You can see comparatively a single bond bromine to fluorine, 237, a little less for bromine to chlorine, and a little less yet for bromine to bromine. So they get weaker as you go down a column. As you go down, remember that atoms are getting larger. As you go across the period, the bonds get stronger. Remember that atoms get smaller as you go across a row on the periodic table. Now let's take a peek at an actual problem. And I wrote on this, I apologize. I'm going to read through my writing. We have a compound CH4 plus Cl2 giving CH3Cl and HCl. And what's nice is that they've actually drawn for us the structural. On the left side, I can see that a carbon to hydrogen bond had to be broken. Carbon to hydrogen bond is 414. That's where they're finding this value. Bonds broken end up to be endothermic, positive value. I also had to break a chlorine to chlorine single bond. And again, using our chart, chlorine to chlorine's on the bottom of the second middle column there. 243 kilojoules. The sum of all the bonds breaking is 657. Over on the product side, I had to create a carbon-chlorine bond. It was a carbon to hydrogen. On the product side now, it's carbon to chlorine. Carbon to chlorine, 339. Notice the negative sign is being placed there because now the bonds are making, and that's exothermic, negative value. We made an HCl. HCl, again, I just look up, hydrogen to chlorine is 431. Report that as negative because it is forming a bond. Those are exothermic. The total energy then in an exothermic value, 770 for the product side. The sum of all the bonds broken, 657, notice bonds broken, endothermic value for the reactants, plus the exothermic sum for forming new bonds gives us a net heat of reaction of negative 113 kilojoules. This is an exothermic process overall. Energy was released during the course of this reaction. Estimating the enthalpy change of a reaction from bond energies. This is just a picture of what we went through. Methane plus chlorine. To break the bonds required energy. We input energy, so it went up positive value. So now we've broken a bond. I see hydrogen has been broken and the two chlorines have been broken apart. We then make bonds. We form a carbon to chlorine and a hydrogen to chlorine. That is an exothermic process. The overall change from the amount of energy input and the amount of energy let go ended up to be a net negative. Overall process was exothermic. Our first question says, calculate the heat change, that's delta H, for the formation of nitrogen monoxide from its elements. We are being asked to turn those words into a balanced equation, and that balanced equation then becomes our target equation. We are forming nitrogen monoxide. To form, we need to point at it, creating a product of nitrogen monoxide. Listening to those prefixes and letting that guide our NO for nitrogen monoxide. And the elements that it's built from both belong to the Lucky 7 diatomic club. Nitrogen and oxygen will be written in molecular form N2 plus O2. And of course, to balance our equation, we'll need to have 2 units of NO. The target equation we are being asked to build will be N2 plus O2, forming 2 units of NO. We'd like to know the heat change for this equation. What is the value of delta H? What we do know are the following elementary reactions. In our first equation, I'm reading 4 units of NH3 react with 3 units of O2 to form 2 units of N2 plus 6 units of water. Its delta H is given as negative 1530 kJs. Our second elementary reaction, 4 NH3s plus 5 O2s yield 4 NO and 6 H2Os. We are being asked to use these 2 elementary reactions, equation 1 and equation 2, so that somehow when we add them together, simplifying what we can from the left and the right, that it indeed forms the target equation that we just wrote in that combination pattern. The target is to build 1 unit of N's plus 1 unit of O's to produce 2 units of NO. For no particular reason, then it's written first. I start using my elementary reactions to find the first reactant in the target. Where do we see N2 written in our building blocks, in our elementary equations? Well, I notice in the first elementary reaction, I'm seeing it written, and it's in a unique spot. That's very helpful in determining what to do with that first elementary reaction. I notice that N2 is on the wrong side of the arrow as compared to my target. And I'm noticing that it's twice as big as I'd like it to be. I have a hunch that I'm going to flip the direction and I'll need to cut it in half. Again, my reason, I'd like to have 1 unit of N2 on the reactant side, but where I'm seeing it is on the product side and it's twice as big as I'd like it. If I flip it and cut it in half, I might have just what I need. Again, I'm not showing work yet, I'm just simply thinking out loud, brainstorming a strategy. The next reactant is the O2 in the target equation. What I'm noticing is the O2 appears in both elementary reactions. It's not very helpful if it's appearing in both. I'm not going to gain insight into what to do with that second elementary reaction. I'm going to choose to ignore that for right now. I'm not finding it in a unique place. More interesting is the placement of our product NO. I'd like to make 2 units of NO in our target equation. Where might I find NO in the elementary reactions? Well, I'm finding it in the second equation right here as the listed of the first product. I like the side that it's placed on. It's on the product side as I desire it to be, but 4 units of NO is twice as large as I'd need in my target equation. I only need to produce 2 units and I have 4 in the target. Again, thinking out loud, I'm going to divide this by 2 or cut it in half, whatever you think of in terms of being easiest for you. Cutting in half, dividing by 2, we'll need to do both of that. Flip the first, cut it in half, and then simply cut the second one in half. Let's see what that gives us. Let's rewrite the strategy so far. We decided in our first elementary reaction, rewriting it in the opposite direction, taking only half the amounts. So the original products now become the reactant. We had written 2 units of N2. Let's cut that in half. We'd now be left with 1 unit of N2. Plus, we started with 6 units of water. Cutting that in half gives us 3 units of H2O. Then we see the yield sign. On the original reactants, now writing them on the product side, we started with 4 units of ammonia. Cutting it in half, we're down to 2 units of ammonia, NH3. Up here, we started with 3 units of oxygen. If we cut that in half, let's write that as 3 halves of O2. The delta H for this new equation will be found by looking at the first value given, negative 1530. Since we flipped to the direction, we need to make it positive, and we also cut it in half. We need half the value. Let me hit on the calculator. 1530 divided by 2, and I find that to be 765. Half the amount and the opposite sign give us the new delta H for our elementary reaction. The second equation, we decided to leave the direction alone, but to cut it in half. We started with 4 units of ammonia. Cutting that in half leaves us with 2 units of ammonia. The next reactant written is 5 units of O2. When we cut that in half, we would write that 5 halves of O2. Leave it in the fraction form. The next product listed is 4 units of NO, but cutting that in half leaves us a net of 2 units of NO. And finally, 6 units of water cut in half gives us 3 units of H2O. The delta H for this new equation would simply be half the amount of the original value. Let me hit that. 1170 divided by 2 is 585, still remaining negative, but half the amount. Hess's law of summation. If we add our two equations together, simplifying what we can, let's prove to ourselves we indeed have made the target equation. What could cancel? I'm noticing in the first reaction I made 2 units of NH3. And in the second equation, 2 units of NH3 are being used. A product on one side cancels the reactant on the other. The ammonias are gone. I also notice in the first equation I have 3 waters written on the reactant side, and in the second equation I have 3 waters written on the product side. 3 H2O's on the left will cancel with 3 H2O's on the right in the next equation. The waters are gone. I'm also noticing O2 appearing on both sides. On the first equation, we have the amount of 3 halves. In the second equation, we have the amount of 5 halves. That can be simplified. 5 minus 3 is 2. 2 halves is equivalent to writing 1 unit of O2. If I take out the product side in the first equation, 3 halves O2, and I simplify with the 5 halves that was written, 5 minus 3 would give me 2 halves. 2 halves is equivalent as 1. And look what we've done. We have taken N2 plus 1 unit of O2 to form 2 units of NO. And that indeed is our target equation. The only thing left to do is to add the new values of the delta H's. Positive 765 plus a negative 585 gives me a total value of positive 180 kilojoules. The value for our target equation we were solving for, 180 kJs, an endothermic value. Let's look next at practice test A, the second question with Hess's law. Our target equation has us looking at P4O6 as a solid plus 2 units of oxygen O2 forming P4O10 in a solid phase. This is what we would label as our target equation. We have 2 elementary reactions to build our target. Elementary reaction 1 has P4 as a solid plus 3 units of O2 as a gas, forming P4O6 solid. And that second elementary reaction, P4 solid plus 5 O2s yields P4O10 solid. For no other reason than it's written first, in my target equation, I generally start looking to find my first reactant. Where might I look to find the first reactant, P4O6? And again, just start skimming through the elementary reactions until you locate it. Here I have it at the first equation at the end, listed as a product. What I like about it is that it has the correct number of units. There is a 1 which matches the target value. We need a 1. But what I don't like about it is the side of the arrow it's on. In my target, it appears as a reactant, but in the elementary reactions, it's appearing as a product. Thinking out loud of a strategy, I think I need to flip the direction of the first reaction. I notice the second reactant is oxygen, O2. I'd like to end up with 2 units of O2. But the O2 appears in both elementary reactions. It's not in one unique place. the O2 is not something I would choose to make a decision on what to do with these elementary reactions. Let's instead focus on the product P4O10. P4O10 appears as a product in the second equation. Again, I'm going to ignore the O2 because it's not in a unique place. The P4O10 is unique. It's uniquely placed as a product in the second elementary reaction. Here's what I like about that. I have the correct number of units. In my target, I need to produce 1 unit of P4O10, and the target equation has just one, so does the elementary reaction. And it's on the correct set of the arrow. That tells me I should leave this alone. So far, I've just been sharing a strategy. Let's indeed prove to ourselves that by flipping the first, leaving the second one alone, we have indeed built our target equation. Let's rewrite elementary reaction 1, but flip its direction. The original product, P4O6, now becomes the reactant. And the original reactants now are on the product side. P4O6 points at P4 plus 3O2. The delta H for this equation, simply flipping the sign, it now reports a positive 1640.1 kJs. We decided to leave the second elementary reaction just as it appears. I'll simply rewrite P4 plus 5 O2s make P4O10. The delta H remains the same value, negative 2940.1 kJs. If we indeed add these together, simplify what we can. I notice that P4s are on opposite sides of the arrow, a product in equation 1, a reactant in equation 2. They will cancel one another. I also notice that on the right side of our first equation, I have 3 oxygens, and on the left side of the equation, in the second, I have 5. If I simplify, I can get rid of the 3 O2s, leaving me a remainder of 2. 5 minus 3 simplifies to 2 units of O2. And indeed, we have built P4O6 left over from that first equation, and 2 units of O2, the remainder of our second equation, forming the desired product of P4O10. When I add together elementary reaction 1, its heat, with the elementary reaction 2 of its heat, we'll find our final answer. So let's hit positive 1640.1 plus a negative 2940.1. I get a value of negative 1300 kilojoules, an exothermic value. With Hess's law of heat summation, we are being asked to find the enthalpy change of what we call our target equation, given the elementary reactions to build from. What we're trying to do is somehow add the 2 equations below so that they create the target equation. And once we do that, we simply add their values of delta H to find the target. Whatever we do to the elementary reaction, we do the same thing to the target. IF plus F2 given IF3, its value of delta H provided. IF plus 2 fluorines give IF5, its delta H is provided. We have 2 building block equations to create the target. IF5 yields IF3 plus F2. I simply turn my attention to the first reactant in our target equation and start skimming through where I find the IF5 in the targets. I'm noticing that IF5 is given to me in the second equation, and it's a unique place There is only one location of IF5. What I'm noticing is I have the right number, but it's on the wrong side of the arrow. I'm predicting that we'll need to flip or reverse the reaction for number 2. And when I do that, I know I need to change the sign. The second ingredient listed up here in the target is the IF3. IF3 appears uniquely in that first target equation. I like the number I have, and I like the side of the arrow I'm on. I bet we just leave that alone. Let's rewrite, finally showing the work we would be required. Leaving the first one alone, we'll just simply rewrite it. IF plus F2 yields IF3. Delta H has stayed the same at negative 390 kilojoules. When we rewrite that second equation, we'll flip its direction. IF5 now yields IF and 2 fluorines. Since we flipped the direction, the sign now is positive 745 kilojoules. I'm noticing here I can cancel out a fluorine, leaving me a net remainder of 1 fluorine on the product side of our second equation. I'm noticing here that IF cancels and leaves no net remainder. And indeed, we have created what our target asks us to find. We have IF5 yielding IF3 and 1 unit of F2. All that we need to do now is add those two values of delta H. Negative 390 plus positive 745 gives us an endothermic value of 355 kilojoules. The value for our target equation, positive 355 kJs.